Good afternoon, everybody. So today's Samvaad-Talk will be given by Professor Arti Yardi. So she has joined as an inspired faculty fellow IIIT-Bangalore since 2019 January, and she received MTech and PhD degree both from IIT Mumbai. She finished that in 2017. Then she went to the as a postdoctoral researcher in the Informatics Research Institute as Toulouse, France, and there she spent from 2017 to 2019. She worked before in Larsen and Toubro at Mumbai from July 2007 to 2009. And today's Samvaad talk she will be delivering on classical and modern channel coding theory. So let's welcome Professor Arti for this wonderful talk. Thank you.
Thank you, Priyanka, for the introduction. Very good afternoon to everyone. Firstly, I would like to thank IIIT-Bangalore for providing me this opportunity to present my work. And I would like to thank every one of you for taking out time for this talk. So in today's talk, I will talk about some problems that I studied during my PhD and postdoc. These problems are in classical and modern channel coding theory. So here is a brief outline of my talk. First, I will introduce a very basic theory to the notion of these channel codes. These channel codes can be broadly divided as classical channel codes and modern channel codes. And then I will discuss some problems that I studied. Now, here is our typical digital communication block diagram. The messages that are to be transmitted are first compressed using the source encoder, and these compressed messages are then encoded using the channel code. And as we all know, these channel codes are essential to have a reliable communication in this digital communication systems. These codes help to correct the errors that are caused due to the channel. Hence, these codes are also called as error correcting codes. Let me give you a very simple example, which probably all of us know, which is a 3 repetition code. In this code, the encoding consists of repeating any bit 0 or 1 3 times, hence the name 3 repetition code. These code words are then modulated and transmitted over the channel. Here I consider the noise is introduced by a binary symmetric channel, abbreviated as BSC. For the BSC, we don't need to consider the modulation and demodulation part. For the BSC, simply flips any of the transmitted bits. Hence, at the receiver, we can receive any of these 8 possible messages because any bit can get flipped. Now, as one can think that the optimal decoding rule is the majority decoding rule. So, for example, here for these 4 vectors, 0 is in majority. So, if we receive any of these 4 messages, then we will decode it as that 0 is been transmitted, and similarly for the 1. Now, in general, we can have a k bit message. Here we have k is equal to 1, and the code word can be n bit. Here we have n is equal to 3, and the rate of this code is defined as k by n. Now, this repetition code is very simple. In general, we can have a variety of mappings which can take us from the messages to the code words, and any possible mapping will lead to a different type of channel code. Now, in 1948, Shannon revolutionized this theory of digital communication. He provided some fundamental limits which one can hope to achieve for the given system. Now let us consider what limit he proposed for the given channel encoded system. Now here R is the rate of the channel code, and the code words are transmitted through a channel whose capacity is C. Now for many popular channels such as binary symmetric channel or binary erasure channel, we can compute the exact value of this C, not always. Now for such a system, Shannon's channel coding theorem says that if the rate of the channel code, if it is less than the capacity, then he guarantees that there exists a sequence of rate R codes using which reliable communication with very low decoding error is possible. Basically what this theorem saying is that if my rate is less than the capacity, then I can have reliable communication. There will be some code which will allow me to have good reliable communication. Now for this talk, I will consider an equivalent formulation of this statement. Now suppose we have an ensemble of rate R codes. That is, we have all possible channel codes of increasing length, but the rate of these codes is R. Then for such a set, reliable communication is possible for all those channel parameters which are less than the parameter which corresponds to the capacity threshold. Now this equivalent notion is a bit unfamiliar, so let me illustrate it via an example. Consider a binary erasure channel. For this channel, the channel parameter is the erasure probability of the channel, and which goes from 0 to 1. Now when the erasure probability is 0, of course we can have reliable communication. Now let's start increasing this erasure probability. Now then the Shannon's theorem says that as we keep on increasing this erasure probability, it reaches till a point called as capacity threshold, such that beyond this threshold we simply cannot have reliable communication. Now one thing I want here to note that Shannon said that okay, I can choose my channel code of rate which is very close to the capacity and can still achieve reliable communication, and such a code is in fact called as capacity achieving code. But he did not say how do I design, how do I construct such a code. Those who are familiar with the proof of Shannon's coding theorem, basically the proof outline says that the capacity achieving code should have a very large length, ideally infinite. Then I can choose any random code randomly from this set and it will be good enough. But then for such an infinite length code, its encoding and decoding will become very difficult. Hence, since the era of Shannon's, people have been trying to design codes which are capacity achieving as well as their encoding and decoding is manageable. Let us briefly see what all scientists have tried to do since 1948 till today. The very first family of channel codes was given by Richard Hamming, and these codes are called as Hamming codes. Of course, these codes are not capacity achieving, but what is good about these codes are their encoding and decoding was very efficient. Then after that, for along 1 decade, people gave various algebraic codes, and some of the notable contributions are Reed-Muller codes, convolutional codes, BCH codes, and Reed-Solomon codes. Now, towards the end of this decade, Robert Gallagher invented LDPC, which is low density parity-check codes. Now, the good part about these codes is the performance, the theoretical performance of these codes was very close to the capacity as compared to these algebraic codes, but it was not possible to implement these codes with the hardware capabilities that were available in 1960s, and these codes were this very good family of codes was actually ignored for a long time. And for next 2 decades, people suggested various efficient encoding and decoding algorithms for these algebraic codes. Some of the notable contributions are Viterbi decoder, BCGR decoder, some efficient decoding algorithms for BCH codes, and people developed the theory of cyclic codes. And in this talk later, I will talk about some problems that are studied related to cyclic codes. And then one of the notable contribution in 1980s is trellis-coded modulation invented by Bock. So in this TCM, the idea was to provide codes with combined coding and modulation. Then another notable contribution in this era is the belief propagation or BP decoding. Now this BP decoding along with the graphical representation of codes led to rediscovery of these LDPC codes. People literally reinvented these codes and they realized that, oh, these codes were actually invented some 30 years ago. So this is the era of classical coding theory. Now, along with the rediscovery of LDPC codes, people invented a new family of codes which is called as turbo codes. Now, these turbo codes are the first capacity achieving codes. I mean, people could not prove that they are achieving capacity, but via simulations they observed that their performance is very close to the capacity. And then for the next decade, people gave various constructions for LDPC codes as well, which could achieve capacity. And one of the notable family that I want to stress here is LDPC convolutional codes, invented by Fellstrom and Ziegengerau. Another notable contribution is polar codes that were invented by Erken in 2007, and polar codes were proved to be capacity achieving, and polar codes are the first channel codes which were theoretically proven to be capacity achieving. But for this talk, I will focus more on these LDPC convolutional codes because I work on a problem which is related to these codes. Now, again, these LDPC convolutional codes, they perform very well. Their encoding decoding was very efficient. And for next 10 years, people were actually trying to understand, they were trying to study why these codes perform so well. And the answer to this question was given in 2009 by Kudekar, Richardson and Urbanke. And they proved that there is something called a spatial coupling phenomenon. And this phenomenon allows LDPC convolutional codes to perform exceptionally well. Now, what is this spatial coupling that I will briefly talk about when I will talk about this problem? Just to complete the historical perspective, from 2009 till today, people have been trying to provide various constructions of spatially coupled and polar codes. I would like to motivate with some applications where these codes are used. The cyclic codes are popularly used for burst error correction. Burst error means if we have a long packet of data, then the errors occur in the vicinity. They occur in chunks. And the cyclic codes are very good in correcting such type of codes. Then they have also been used in internet data packets. A variant of cyclic codes, CRC codes, which is cyclic redundancy check codes, are used in internet data packets. Then convolutional codes are used in mobile communication. Then serially concatenated convolution and Reed-Solomon codes are used in satellite communication. Then LDPC codes are popularly used for satellite communication in digital television. They have been standardized for various telecommunication standards. In the wireless communication, they have been used in 4G, 5G, and also Wi-Fi 802.11. Then turbo codes are used in wireless communication. They are used in 3G, 4G, and also they have been used in NASA's Mars mission. And more recently, polar codes have been standardized for upcoming 5G wireless standards. Now, other than these mobile and satellite communication applications, here are some unconventional applications of channel codes. The first application is coding for data storage. So, these big companies, Google, Facebook, they store their data along the way, multiple servers. And for storing data and recovering data from these multiple servers, channel codes are used. These codes are called as regenerating codes. Then a family of channel codes, GOPA codes, are used in cryptography. Then channel codes are also used for storing the data on the non-volatile memories. They have also found applications for designing fault-tolerant circuit systems. And most surprisingly, they also have found some resemblance with the structure of DNA sequences. So these days people have been trying to find the similarities or trying to study the DNA sequences using the channel codes. Now with this very brief introduction of channel codes, I will now move to my first problem. The title of this problem is blind reconstruction of binary cyclic codes. I studied this problem during my PhD, and this is a joint work done with my advisor, Professor Sarvanan Vijaykumaran and Professor Animesh Kumar at IIT Bombay. Now first I will introduce what is this problem of blind reconstruction of channel codes. Now our routine system, we have a channel encoder at the transmitter, we have a channel decoder at the receiver. But in this problem, we consider a scenario where there is an eavesdropper. And this eavesdropper does not know which channel code is used at the transmitter. So, for example, such situations may arise in military communication when the channel code used by an adversary, used by the enemy might not be known at the receiver. So, in such situations, eavesdropper has an access to the noise affected sequence of the message bits, but he does not know which channel code is used. Hence, the aim is to reconstruct the channel code or identify the code that is used at the transmitter given access to the noise affected code words. Hence, the name of this problem is blind reconstruction of channel codes. Now, this problem is known to be NP hard. Of course, I mean, imagine that you don't know anything about the channel code that is used at the transmitter, and you are trying to guess which channel code might be used, and it can be potentially any code. So this problem is proved to be NP hard. So typically what people do is they assume that the channel code that is used at the transmitter belongs to some known family of channel codes, say convolutional code or LDPC codes. And then under this assumption, they try to guess which code might be used at the transmitter. So in this work, I will assume that the channel code that is used at the transmitter is some cyclic code, and my aim is to identify the correct cyclic code. Now I will recall some basics of cyclic codes. Cyclic codes, every cyclic shift of a code word gives me a valid code word. Let us consider an example. This is a cyclic code. This is an example cyclic code of length 4. Here observe that if you take cyclic shift of any code word, it gives me another valid code word. Now for cyclic codes, code words and messages are conveniently represented using polynomials. Let's consider an example. For example, this code word 0101, its polynomial representation is x square plus 1. Here the LSB corresponds to x to the power 0 and so on. Now these cyclic codes have a property that any code word polynomial v of x can be written as a product of u of x and g of x, where u of x is a message polynomial and g of x is the generator polynomial, and this generator polynomial is common to all possible code words. Let us see our example. Now let us factorize the polynomial representation of all code words. So for example, here v3, which is x cube plus x, can be factorized as x into x square plus 1, and this x square plus 1 is common to all 4 code words, and it is the generator polynomial. Now I would like to highlight on one important property of the cyclic codes. This property is that for a cyclic code of length n, this generator polynomial is a factor of x to the power n plus 1. Let us see our example. X to the power 4 plus 1 can be factorized like this, and here we can see that our generator polynomial x square plus 1 is indeed a factor of x to the power 4 plus 1. Now the only takeaway from this slide that I would like to highlight is for the cyclic codes, this generator polynomial is common for all code words, and this g of x is a factor of x to the power n plus 1. No, it might need not be known. Yeah, it is possible, but the model that I consider that eavesdropper is not causing any trouble, so he's just listening. He's not allowed to enter any extra bits. And yes, like you said, that the length is not known, the generator polynomial is not known. In fact, that's what we need to identify in this problem. Yes, so here I consider the noises introduced by BSC. So for the BSC, we can guess that average amount of errors, bits that might get affected. But we can only guess the average amount of bits. Potentially it can be anywhere. We come back to our problem for the blind reconstruction of cyclic codes. So here CN0G0 denotes a cyclic code of length N0 and generator polynomial G of x. Noise is introduced by a BSC of crossover probability P, and we receive the sequence. Now note that, like you said, it is these parameters are not known to us, and for the blind reconstruction problem, we need to precisely identify these two parameters. Now again, we can factorize this generator polynomial as the product of some irreducible polynomials fi of x raised to their multiplicities. And for blind reconstruction, we need to identify these irreducible factors as well as their multiplicities. Now first we will consider the case, very simple case, when the length of the code is known to the receiver but the generator polynomial is not known. And we assume that the received data is perfectly synchronized, meaning code word boundaries are known to the eavesdropper. Now let us see how do our received sequence will look like when the length and the synchronization are known. Yeah.
So what is the motivation of using generated product of
Actually, the motivation is because I know the generator polynomial will be a factor of x to the power n plus 1. So I can collect all possible factors of x to the power n plus 1 and check whether each and every factor, is it a factor of generator polynomial or not. So we can. Yes, so it's not necessary. This is what I am doing. Yes. No. This is in fact very unique to the cyclic codes. And that's why for the cyclic codes we can actually, as we will see in the later slides, we can have very nice structure and everything, which did not be possible for an arbitrary linear block code. So now suppose V1, V2 and so on are my transmitted code words of some cyclic code. I just know the length of this cyclic code, not the generator polynomial. Now after the introduction of the error, suppose y1, y2 and so on are my received polynomials. Now suppose we know a candidate polynomial f of x. Then for this candidate polynomial, we just now need to decide whether is it a factor of generator polynomial or not. So the problem gets reduced to a simple hypothesis testing problem, where for a given factor we need to make a decision between these two hypotheses. Now we just, as we discussed, for the cyclic codes, we know that the set of factors for the x to the power n0, where n0 is the true length of the code, is the possible candidate set for the factors for the generator polynomial. So in this problem, basically we can imagine that we have a bag which contains all possible factors of x to the power n0 plus 1, and we will take out each factor from this bag at a time and decide whether is it a factor or not. So now to take this decision, what we do is we consider these syndromes or the remainder of the received polynomials with respect to the given candidate factor f of x. Here rj of x is the remainder which we obtained after dividing yj of x using f of x. And then we study the distribution of this syndrome to take a decision between h0 and h1. Now again we have two possible scenarios. So we prove that when f of x divides g0 of x, then the zero syndrome is more likely than any other non-zero syndrome. Now let's consider a simple scenario when the crossover probability is 0. When the crossover probability is 0, my yj is equal to the code word always. So the code word is always a multiple of g of x, and whenever f of x is a factor of g of x, v of x mod f of x will be 0, and probability that rj, the syndrome is 0 will be 1. Now when crossover probability is not 0, the syndrome distribution will look like this. Now here there is a key property of this distribution that whenever p is strictly less than half, the zero syndrome is more likely than any other syndrome, and this is what helps to identify between the two situations. Now let's see what happens when f of x doesn't divide g of x. Now in this situation we prove that the syndrome distribution will be uniform. Even with the introduction of error, the syndrome distribution continues to be uniform. So here we can see that the syndrome distribution is different depending on whether f of x is a factor and not, and this is what helps us to identify the two situations and solve the blind reconstruction problem. Of course, once we have identified the irreducible factor f of x, we need to identify its multiplicity. For that also we study similar syndrome properties that I will not discuss. Now let us move on to the problem where the eavesdropper doesn't even know the length. Here another important catch is that it may so happen that the eavesdropper starts observing data in between. So in this situation, this y0 need not be the first code word bit of any cyclic code. So what we do is we begin by assuming some length n, and then we assume some synchronization s and ignore initial s bits in this sequence. And for the assumed length n, we divide the remaining sequence into vectors of length n. Now here y1 of ns is the first received vector of length n with assumed synchronization s. Now suppose y1 of x is the polynomial representation of this first polynomial, and so on. Now again for the blind reconstruction problem, here we need to identify the correct length, correct synchronization, and the generator polynomial which is again factored like this. Now for the assumed length n, again the set of all possible factors of x to the power n plus 1 becomes my candidate set for the factors of generator polynomial. Now in this situation, let's see how do my received data will look like. Now here code word 1, code word 2 and so on are the true code words, the code words of the true code that is used at the transmitter. The length of this true code is n0. Now since we don't know this length, let us try dividing this data according to some wrong length. So suppose that my assumed length was more than the true length. So here we can see that in this situation, any vector of length n is formed by some parts of the code words of my true code. For example, here this vector is formed by part of code word 2, code word 3 and code word 4. Even when n is less than the true length, at that time also my vectors are, my n-bit vectors are formed by the parts of true code words. Now note that this is a noise-free data. What we observe is the noise-affected version of this. Now in this situation, again we formulate this as a hypothesis testing problem, where under hypothesis H0, my assumed length is correct, my assumed synchronization is correct, and f of x divides g of x. And under hypothesis H1, some of the assumed parameter is not correct. So in this problem, the main challenges are to come up with a statistics which will allow us to distinguish between these two situations. And of course, we have to be sure that, okay, my method will indeed be correct. So we have to guarantee some correctness. Now here I will denote the polynomial corresponding to the noise-free vector as my w of x. Now ultimately we use the similar approach, the syndrome distribution. Now here y, which is the noise affected version of w of x, which is the noise-free n-bit vector. Ultimately we want to study the distribution of the y of x mod f of x, but in order to do that, we first study the distribution of w of x mod f of x. Now, we prove that whenever my assumed length is not correct, at that time, the distribution of this noise-free syndrome can either be uniform or it can be restricted uniform. Now here, note that this distribution is again uniform, but some of the syndrome entries are missing here, hence we call it restricted uniform. So first we prove that the distribution of noise-free syndrome can either be of this type. We also provide some necessary and sufficient conditions that when the distribution of will be uniform and when will it be restricted uniform. And the conditions are on the assumed length and assumed factor, which I will not go into the details. Now what we want to do is we want to study the distribution of noise affected vector. Now we saw that the distribution of w of x can either be uniform or restricted uniform. Now let us try to guess how will the distribution of y mod f of x will look like under the condition we know the distribution of w mod f of x. Yes, the distribution is in restricted uniform. First of all, some of the entries are missing, and whatever entries are present, the distribution is uniform over that support set. Yes, I assume that any code word is transmitted with equally likely distribution.
But yeah, so what extent is
No, it is completely uniform. So if I assume that my transmitted code words are uniform, that any code word is chosen with uniform probability, then the distribution of any n-bit noise-free vector will be of this type. So it doesn't matter, because like in the last slide we saw that the n-bit vectors can be of a variety of types.
So what I do not want to how do you use code words that are non-uniform?
It may help. I mean, if we want to consider this problem from the other point of view, that I don't want adversary to guess, but it may help. But at least when it is when the code words are equally likely, in fact, I can say that okay, I can easily identify the code. So I would say that if you don't want the adversary to guess your code, do not use cyclic codes. That's how I will portray. Okay, so now when the distribution of w of x is uniform, okay, let's try to guess how will the distribution of noise affected syndrome will look like. So now will the distribution look like this? Any guesses? Yes, in fact, when the distribution of noise-free vector is uniform, the distribution of noise-affected vector is also uniform. This is what we prove. Now, in this situation, let's try to guess the distribution of noise-affected. In this case, will the distribution be like this? Any attempt? In fact, the answer is no. The distribution will not look like this. We prove that the distribution will look like this. And in fact, we prove that finding this exact distribution becomes computationally intractable. But however, even though finding these exact values of this distribution becomes computationally intractable, it again has some structure that the entries which were present in the noise-free distribution, those entries continue to remain more likely than the other entries. So we make use of some such properties and provide a blind reconstruction algorithm. And in fact, we also provide some bounds on these values, and that enables us to provide a theoretical analysis of our method as well. That I haven't discussed here. But here I would like to discuss one thing which was like, so while studying this problem, we identified some new structural properties of this cyclic codes, and I would like to mention one of the structural property that we identified. Okay, so now let's see what this structural property is. Now suppose we have the code words of a cyclic code. Here V1 to Vk, suppose these are the code words of my cyclic code. Now let's choose some integer n1 and consider the polynomial corresponding to the initial n1 bits of all these code words. Now, if I assume that the polynomial corresponding to this blue part is a multiple of some h of x, then we prove that then such a cyclic code will be a degenerate code. What do I mean by degenerate? Meaning that the generator matrix of this cyclic code can be written as concatenation of some another generator matrix G prime. And in fact, such a code is not a very good code in the literature. Now, I have just stated this property in the form of lemma, which says that my cyclic code is a degenerate code if there exists an integer n1 such that the polynomial corresponding to the initial n1 bits of every code word in this code is a multiple of such h of x. Just the pictorial representation of this lemma. Let's see some simulation results. First, for the known length and synchronization case. Here on the x-axis, we have increasing values of crossover probability for the BSC, and on the y-axis, we have probability of detection. Here, blue curve is for our proposed method, and red and black are for the existing method. Here, we can see that the probability of detection of our method is always greater than the existing method. Here is another simulation result for the unknown length synchronization scenario. Here also again we can see that the probability of detection of our method is better than the existing method. Now I'll summarize the contributions for this problem. So for this blind reconstruction problem, we studied the distribution of syndromes of the received polynomials. For the known length and synchronization case, and when there is no error, we proved that the syndrome distribution will look like this, and with the introduction of error, the distribution will look like this. For the unknown length and synchronization case, when all the parameters are correct, the distribution looks like this, and when either of the parameter is not correct, the distribution will either this or this, and with the introduction of error, this distribution will look like this. And this ends and we also provided use these properties to provide our blind reconstruction method. Now I will move on to the second problem. Actually, I didn't talk about that part. So basically, I formulated as a hypothesis testing problem. Then in the statistics, various methods are available which will allow you to do this problem and handle and give the solution systematically. So actually, I didn't explain it. Yes. 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 This method is independent of which message is used. So I just aim to find the generator polynomial, and once it is known, the decoding can be taken care of separately.
Yeah, but that's still a non-trivial.
Yes. Yes, that is a different problem.
Here you are only finding.
Yes, yes. So my aim is only to identify the generator polynomial. That's it. In fact, there are some papers which talk about the joint decoding and the identification. So there are some papers in the available in the literature which consider the problem which you are talking about, but here I am not considering that problem. So I just assume it is some cyclic code. Then I have to use another method, because if it is not a cyclic code, then of course the code will not have a generator polynomial, and then considering the factors of x to the power n plus 1, all these things will not be applicable.
This problem you said is actually hard problem.
Yes.
We have a class of code for this, you know how to identify this code identity.
Yes, so people have studied this problem for LDPC codes. Then I think they have some good analysis for the convolutional codes as well. But for a large variety of possible channel code families, this problem has not been tackled yet. For example, I feel that, for example, the way cyclic codes are very rich in algebraic structure, the Reed-Muller codes are very rich in structure. So even for the Reed-Muller codes, we might be able to see some similar nice structural properties, but it's not been studied in the literature. Okay. Now with this, I will move to the second problem, which is the last problem. This is the problem which I am working currently. So this problem is estimating the map which is maximum a posteriori threshold for the families of sparse graph codes, which are LDPC codes and turbo codes. And I worked on this problem during my postdoc work. This is a joint work done with my postdoc advisor, Professor Charlie Pulia, Professor Tariq Benadi, and Professor Irina Andrianova. Now, the flavor of this problem is totally different from whatever we have been seeing till now, because this is a problem in modern channel coding theory. The way we look at the problems in classical coding theory and modern channel coding is totally different. In the classical, we have very nice algebraic structure, we have nice properties, but we cannot talk about similar quantities for the problems in modern coding theory, because the length of this codes is typically very, very large. So I will now, before I talk about this problem, I will introduce some very basics of LDPC codes. Now the LDPC codes, which are low density parity check codes, are conveniently represented using bipartite graphs. Now in this graph, we have variable nodes on the left hand side. Here V1 to V5 are variable nodes, and on the right hand side we have check nodes C1, C2, C3. Here length of the code is 5, and each VI can either be 0 and 1. Now what do check nodes imply? Now for example, to this C1, V1, V3 and V5 is connected. So this check node C1 implies that these variable nodes should satisfy the parity check equation, that it should satisfy this constant that V1 plus V3 plus V5 should be equal to 0. Of course, the addition is binary. Similarly for C2 and C3. And all possible code words in an LDPC codes are all those possible combinations for each VI which satisfy these three parity check equations. Of course, the real life LDPC codes are very large, where this V5 is some 10,000 or 20,000, and it similarly has large number of check equations. But why they are called as low density parity check equation is the number of entities in every check equation are limited to 3 to 4. Hence, overall, if we consider the parity check matrix of this code, it looks very sparse. Hence, it is low density parity check code. Now, here this parity check equation C1 corresponds to a single parity check code. Now, in general, if it corresponds to any arbitrary code, say Hamming code or BCH code, then such an LDPC code is called as generalized LDPC code. Similarly, here the variable nodes corresponds to repetition code, and whenever it corresponds to any general code, it is called as doubly generalized LDPC code. Now, typically we consider a collection of LDPC codes, because we cannot study the properties of LDPC codes taken one at a time. So we have to consider a collection, and this collection is typically identified using its degree distribution pair from node and edge perspective. It's very simple. Let's consider an example. So here we can see that every variable node has a degree 2. So its node degree distribution from node perspective is x square. similarly for check nodes, we can see that C1 and C2 have degree 3 and C3 has degree 4. Hence, degree distribution is this, where 2 check nodes out of 3 have degree 2 and 1 check node out of 3 has degree 4. And the collection of all possible LDPC codes which have same degree distribution pair is called as an LDPC code ensemble. So here the lengths of the codes can be different, but what do they have common is this: they have same degree distribution pair. And typically we say that when we say that we have an ensemble, we talk about the properties about this ensemble, not about a particular code which is taken out from this ensemble or the collection. I'll quickly recall very few basic concepts about belief propagation or BP decoding. Now, BP decoding is an iterative message passing algorithm, meaning in one iteration, we pass messages from variable nodes to check nodes along the edges, and we pass similar messages from check nodes to variable nodes along the edges. Now, suppose L1 to Ln are some initial messages that are available with the variable nodes. These messages come from the channel. I will not go into the details of what this message is exactly, but for time being, we can assume that okay, it is some message which will tell you some belief about whether Vi is 0 or 1. That's what we want to predict at the end of decoding. Now, let's see what is the message transmitted by variable node Vi to check node Cj. Initially, Vi will send the initial message which is available at it. In the next iteration, this check node Cj will collect all possible incoming messages, and the message sent by Cj to Vi corresponds to the likelihood of that Vi being 0 or 1 given all the incoming messages at it, but such that the parity-check equation corresponding to it is satisfied. It's a bit complicated, but I just want to say that okay, it receives some messages, does some processing and sends back message to variable node. Similarly, what does the variable node do? It takes the addition of all the incoming messages and sends it back to the check node Cj. So the one iteration of BP decoding consists of message transmitted from variable node to check node and check node to variable node. And we can have many such iterations. Ideally, we can have infinite iterations. But in practice, we restrict it to some few hundreds of iterations to have a practical decoding algorithm. Now, I would like to introduce 3 very important concepts related to a collection of LDPC codes. I will keep recalling these concepts for the remainder of the talk. So, we consider an LDPC code ensemble denoted by C. This ensemble can be specified a given degree distribution pair. Now, we choose a code randomly from this ensemble and send the code words of this code over the binary memoryless channel with the parameter denoted by H. So, for example, for binary erasure channel, the parameter could be erasure probability. Now, I define something called as BP threshold. Now, this BP threshold is defined as the maximum value of channel parameter such that the average probability of error using BP decoding goes to 0. So, recall that ideally in the reliable communication, we want to have 0 probability of decoding error, and this BP threshold is defined as the maximum value of the channel parameter such that I can have a reliable communication using BP decoding. Now, here I allow the number of iterations L in the BP decoding to go to infinity, and also I am allowed to choose the codes of infinite length. Now, the next quantity that I want to define is map threshold. This map threshold is defined as the maximum value of the channel parameter such that the average conditional entropy of the transmitted bit for the infinite length code goes to 0. And then the third quantity that I want to define is capacity threshold. This is nothing but the channel parameter that corresponds to the capacity of the channel. Now, let me give you how these quantities are related through an example. Suppose we have a binary erasure channel. Then of course the channel's capacity parameter will be at the topmost point, and the map threshold will be less than the capacity threshold, and BP threshold will be less than the map threshold. Yes. Yeah, actually similar to demodulation, you can have map decoding as well, which is the optimal decoding strategy. So, for the LDPC codes, they have very large length, so one cannot implement the map decoding. So you can visualize that this map threshold is associated to the map decoding. If at all I am able to do the map decoding, then whatever the maximum value of the channel parameter that I can achieve, that is yes, yes. And BP decoding, it is not optimal, so that's why the BP decoding threshold is less than the map decoding threshold. Now just coming back to our original problem of designing capacity achieving code. If we want to design a capacity achieving code using BP decoding, then we want all these three parameters to be the same. If these three parameters are the same, then I will say that okay, I can achieve capacity using BP decoding, which is really a huge achievement because BP decoding is suboptimal decoding algorithm, and ultimately we want to design a practical which will achieve the capacity. Now I talked about that these days people have been trying to design these specially coupled codes. Now let's see what is this special coupling. Let us bring back our LDPC code example which I had introduced earlier. Now in special coupling, what we do is we consider the multiple copies of the same code. And then in the next step, what we do is we take out some of the edges from one copy and connect it to the copy which is placed adjacent to it. And we keep on doing this. Thus, these code blocks are coupled specially by spreading edges over the time. Of course, we need to take care of the termination, but that's okay. We don't need it for now. And hence, this code which is obtained after special coupling is called as the specially coupled version of the original code. Now, why this specially coupled code is so good, or why at all I should bother about doing this special coupling? And the reason is, Kudekar proved that the BP threshold of the specially coupled code approaches the map threshold of the uncoupled code. So, in simple words, this special coupling allows me to achieve map decoding performance, but using BP decoding only. And that's why this special coupling became very popular in this last decade. And let's summarize whatever I have talked till now. So this one slide basically will summarize whatever basics I have introduced about LDPC codes till now. As we all know, there are some fundamental limits for reliable communication. First limit is given by Shannon, which says that for an arbitrary radar code ensemble, reliable communication is possible if the channel parameter is strictly less than the capacity threshold. Next, suppose if we have a specific code ensemble, not arbitrary, say given by a particular degree distribution pair, then for such an ensemble, reliable communication is possible if channel parameter is less than the map threshold. Now, if we are only allowed to do BP decoding, then the threshold that I can achieve with the BP decoding is called as BP threshold, and reliable communication with the BP decoding is possible if my channel parameter is strictly less than the BP threshold. Now, as I mentioned in the last slide, BP threshold is strictly less than the map threshold, which is of course less than the capacity threshold. Now, if I want to design a capacity achieving code, then its map threshold should approach to the capacity threshold. If I in the last slide we saw that this special coupling allows us to approach map threshold via special coupling. The BP threshold approaches the map threshold via special coupling. So now suppose if I want to design a capacity achieving code via special coupling, then this design process can be divided into two parts. First, I should be able to identify a family of code whose map threshold is close to the capacity threshold, and then I can devise some good methods for the special coupling. Now in the literature, these good methods are already available, and here we try to tackle this first problem, which is finding the map threshold of a given code ensemble. Well, the bad news is finding this map threshold is in general known to be computationally intensive. It's not possible to find. And the good news is Mieso and other people have given an analytical method to find this map threshold. Now, what is this analytical method? It's a very simple method. I'll just have to introduce one chart. Now, this chart is called as EBP-G exit chart. This EBP-G exit stands for Extended Belief Propagation Generalized Extrinsic Information Transfer Chart. So, okay, it's a fancy name. Basically what this chart is, on the x-axis we have channel entropy. For the binary input channel, the channel entropy can go from 0 to 1. And on the y-axis, we have this fancy EBP exit function. Now, what this function does is, it basically characterizes the average entropy or average uncertainty about a given bit. In the decoding, we want this average entropy or uncertainty about a given bit to be 0. Because if my decoding is correct, that means if I am able to correctly identify 0 is indeed 0, then the uncertainty should be 0. And this uncertainty is what this EBP exit function characterizes. And this she-shape function is very typical form of this EBP exit function. Now, what is the speciality of this EBP exit chart? And the speciality is, you can read BP threshold, math threshold, and everything you need to know about this code ensemble readily from this curve. And how do I do that? Now, if I want to find the BP threshold, I simply draw a vertical tangential line, and the point where it touches the x-axis provides me the BP threshold. Now, to find the map threshold, we need to apply something called as Maxwell construction to this EBP exit chart. Now, what is this Maxwell construction? We simply draw a vertical line on this chart, and we stop at the point when this blue part and red curve are same in area. And the point where these two areas are same and where it touches the x-axis gives me the map threshold. So now we are happy. Yes, we have a method to find the map threshold, which was what our problem since the beginning. Well, this problem is solved provided we have this EBP exit chart, and unfortunately it is very difficult to find. So in some cases, yes, we can find this EBP exit chart. For example, for binary erasure channel, it is possible to draw this EBP exit chart for some families of LDPC codes. But in general, for computationally intensive channels such as binary symmetric channel and AWJN channel, finding this EBP exit chart is very difficult, and which is what we do. So what we do is we provide a computationally tractable method to find an approximate EBP exit chart. Finding the exact EBP exit chart is not possible, so we find an approximate curve and then predict the map threshold. And we do this for AWJN channel, and we predict map thresholds for regular and irregular LDPC codes and some generalized and doubly generalized LDPC codes. And then recently I am also extending this method to any general concatenated system such as turbo codes or where the modulation and coding schemes are concatenated. And we estimate the map threshold for these families. So I guess I won't be able to go into the details of how do we exactly find this approximate EBP exit chart, but this is what we do, that we find the approximate version of EBP exit chart and predict the map threshold. Let's see some simulation results. So first we compare it with some available EBP exit chart. So here this is the EBP exit chart which is obtained using the exact method. For some cases it is possible, and this is our approximate EBP exit chart. As we can see that using the approximation we don't really lose much. This is another example. Now then I have EBP exit charts for some generalized LDPC codes, and these are the predicted map threshold and BP threshold values. This is another example for the GLDPC codes. Here just I want to highlight that before this people didn't know how do I find or how do I give an estimate of map threshold of such computationally involved generalized LDPC codes. Then in the next slide I have EBP exit charts for some doubly generalized LDPC codes. I just want to stress that these codes are very complex in structure, and using the exact method it is impossible to find the EBP exit chart, but our approximation allows it. Now for example, this particular example we can see that the BP threshold and map threshold are the same. So this the lower tail of my EBP exit curve is missing here. So it's not advisable to do the spatial coupling for such codes. So our method will be like a precursor. Whether is it should I go for the spatial coupling, or should I spend efforts doing spatial coupling or not? So we get this answer before spending these efforts. Now in this table I have some predicted values of the map threshold. So these are the map threshold which we obtain using the EBP exit chart. The map threshold is mentioned in terms of channel entropy H and the ES by N0 values, and here we have map estimated values. In the right hand column, I have obtained these values by doing the special coupling and very rigorous simulations. Now here we can compare this column and this column and this column and this column. We can see that the predicted values using the EBPG exit chart method are quite close that what we can obtain after the rigorous simulations. So it's safe to say that okay, we can predict map threshold up to pretty good accuracy. Now I'll conclude my talk. So in this talk, initially I provided a very brief historical overview to the theory of channel codes. Then the first problem that I talked about was blind reconstruction of binary cyclic codes. Now in the future, I would like to study this problem when the channel code that is used at the transmitter could be a Reed-Muller code or a Reed-Solomon code or a shortened cyclic code. Also, we consider the model when the channel model of BSC. I would like to consider other channel models such as erasure channel or relay fading channel. Also, we consider the single input and single output system. I would like to study this problem when there are multiple transmitters and multiple receivers, the MIMO system. Then secondly, we studied the problem of estimating the maximum or posteriori, which is map threshold of LDPC and Turbo codes. And in the future, I would like to provide this map estimation method for combined modulation and coding schemes. And also I would like to consider the relay channel model, and also when the interference is present in the noise. Thank you.